Good morning, everyone. Thank you for being here and filling this large room. It's a privilege to be here with you today. I'm from IBM Quantum Research Team. I'm based in Australia, Sydney, and I came to be with you here today. We're going to talk about quantum computing and its promises and also the risks that can come with quantum computing. In IBM research, as you can see here, in quantum research, we have a twofold mission. One of that mission is to bring useful quantum computing to the world and introduce it to our lives so that we can use it in our organizations, in our day-to-day lives, and make things safer, more efficient, quicker, and solve the problems that we are not able to solve today with classical computing. We'll discuss why it is like that. On the other side, as all other technologies, a technology can be used for good purposes and bad purposes. There is also a risk that quantum computers might create a risk for our security, and we'll also touch to that. So, as you can see here, at the top part, in today's world, we have classical mechanics laws, and we have built bits that can be either 0 or 1, and using those bits, we have created all this technology we have today. We have formed CPUs, GPUs, AI processing units recently, and then now we are using this in our day-to-day lives, in our banking systems, in our telecommunications networks, whenever we have on our mobile, our apps, and everything is based on this deterministic bits. On the other side, as you can see at the bottom part of the slide, now there is quantum computing arising, which is totally different, fundamentally different from classical computing. It is based on another types of physics, quantum mechanics. And the basic unit is called qubit. This means quantum bit. And they are fundamentally different to deterministic bits. And bringing qubits together, we form QPUs, quantum processing units. And they will merge. They already started merging. And quantum computing will not replace classical computing. As you can see here, it will merge and it will help classical computing. We will be tackling some difficult problems like optimization problems, simulation problems, understanding what's going on in that atomic level, molecular, chemical reactions. We'll be doing that with quantum computers, and then we'll be loading that information and merging it with classical computers. This is what we call quantum-centric supercomputing. We said quantum qubits are fundamentally different from bits. Let's have a deeper look into that. First of all, it has three unique properties: superposition, entanglement, and interference. Superposition is about qubits taking value of 0 and 1 simultaneously at the same time with a probabilistic distribution between them. Entanglement means like a secret communication channel between two or more qubits. When they are entangled, when we make a measurement in one qubit, you understand the states of other qubits, even if they are millions of light years far away from each other. And interference is about being able to find the probabilistic right results, right outcomes, wanted outcomes from qubits, playing with their microwaves, vibrating frequencies. So what does that mean then? What happens? So I'll give you an example. Imagine that we are trying to find the way out from a maze. There is an input, there is an output, and there are multiple ways in between. When we tackle this problem with a classical computer, what it does, it starts at the entrance, and then it checks. Is right the exit? No. Okay. Then left? No. Okay, then I'll iterate one more. Right? Right. No. Right, left. It goes on like that to check all possible outcomes one after another. But with quantum computers, it doesn't work like that. Imagine a mist permeating inside that maze and covering all possible exits at the same time, and then coming up with the right solution to the problem in one go. Because of that, quantum computers will be solving many difficult problems very quickly, which can transform many industries. We are using quantum computers in solving these types of problems, better understanding chemistry, materials, optimization and search problems, better machine learning, linear algebras, and similar problems. These have many application areas in many industries. For example, banks are using it to better understand the fluctuations in the financial market, or better pricing their products, or supply chain optimization problems, or better medicines, better vaccines. Moderna is using IBM quantum computers to build better vaccines, to understand what's been going on. Pfizer is using to build better medicines. And there are many examples, which we'll cover some of them. Boeing is trying to build, together with IBM, better airplanes using lighter, stronger materials, discovering all these materials by better understanding what's been going on in that atomic level. CERN laboratories. As you know, there are particle accelerators and colliders. This is the biggest particle accelerator in the world. And they are trying to build new, unknown particles using machine learning powered by IBM quantum computers in CERN laboratories. Another example from banking industry. As you can see on the right-hand side, HSBC is using IBM quantum computers for better pricing, better portfolio optimization, and better understanding risk and fraud scenarios, discovering risk and fraud cases amongst millions and billions of interactions out there. So these are just some examples to good usage of quantum computing. As we said in the beginning, it can also create some risks. Now we'll have a look at those risks. Today, for example, when I want to send money using my banking app to my friend, I think that it is secure, right? It is secure. Why it is secure? Because that transaction is encrypted with some security algorithms, encryption algorithms. And a hacker, a pirate, cannot understand what's going on in that encrypted message because it's very difficult to solve. It's based on, mathematical problems that is very difficult to solve using our classical computers. Even if you use the strongest supercomputers today, you cannot find the P and Q numbers here that when multiplied, giving us this large 619-digit big number. This is why it is secure, that sending that message is secure. This is the underlying security mechanism within RSA algorithm. There are similar algorithms that we use in digital signatures. When we sign the document, when we send an update to our IT systems. We all use this RSA, DSA, elliptic curve, Diffie-Hellman type of algorithms that are based on similar problems, since they are very difficult to find the answers with classical computers. Even when you use the strongest supercomputers today, it takes millions of years to understand the key in that banking transaction. But in very close time, in very near future, we are talking about the end of 2020s, 2029, 2030, like 4, 5, 6, 7 years away, based on our estimations, quantum computers will reach a power to break these codes in hours using Shor algorithms, which introduces a big risk. When used with bad intentions, bad actors can gain control to banking transactions. They can manipulate legal history. They can play with digital signatures. They can have access to critical infrastructure. Imagine some pirates, some bad actors gaining access to military radar systems or energy networks or telecommunication networks. They can destabilize financial markets. So the implications are huge. So we are talking about very near future, and this is not tomorrow's problem. This is today's problem, because these attacks started happening today. What they are doing, this is called harvest now, decrypt later type of attacks. They are stealing and storing some encrypted traffic today, encrypted information, knowing that they cannot break them today. But they are waiting. They are keeping them in 5 years, 6 years, 7 years' time, when they will have access to a powerful quantum computer, then all the information that is being kept secret in those, will be revealed. So this is why it is today's problem. When we have a data in our organization, like, for example, health data of people, or transactional data, financial data, or any other data that needs to be kept secret in 10 years' time, 20 years' time, 30 years' time, if you are working with such assets, such important data, then today you're at risk if you're not taking any precautions. But there is a solution to this, because the world has reacted and the solutions have been found. In 2016, White House tasked NIST, American National Institute of Standards and Technology, to come up with the new quantum-resistant encryption algorithms. And they started a competition. They invited all major technology providers. 83 algorithm submissions were made. 3 of them came from IBM. Google gave some, Microsoft gave some, Amazon, Samsung, Nokia, Ericsson, Thales, many organizations, many universities. 83 submissions have been tested for 8 years. And last year, as you can see here, 3 standards have been announced. And 2 of those standards came from IBM submissions. The rest of those 83 weren't found secure enough, good enough, practical enough. For whatever reasons, they were not standardized. So they came from IBM laboratories, and the third one came from a researcher group, an academician group. And the main academician who participated in that research then joined IBM as well. Now, all people who develop world's new standards are working in IBM research laboratories in Switzerland. So this is nothing commercial. These are all open standards, open source code. So we have developed these, and served to the world, and we are very proud of this situation. So when we say that IBM is leading the efforts in quantum computing and quantum safety, we don't think that we are exaggerating based on that information. There are many guidance to adopt these new standards because we have to replace that RSA, DSA, Diffie-Hellman, the standards that we are using today with these new standards that cannot be broken by even with quantum computers. They are called post-quantum cryptography. And World Economic Forum, G7, major consortiums, GSMA, many countries published recommendations. And the world has started moving already, starting from, as you can see here, 2023s, 2022s, in Germany, in France, Singapore 2023. There are moves in all parts of the world. So, some organizations that we are talking to about adopting these new standards, thinking that we don't have a regulation yet in our country. So, if this is the case, that does not mean that you are safe, we are safe. We should not wait for regulations. Regulations will come sooner or later. It came in many parts of the world already. It's been mandated, but not everywhere. So, but the time is running out. We have 4, 5, 6 years to adopt these cryptographic standards, and it's a big task. It's not easy. Imagine all the applications, all the systems communicating in your network, all the source codes you have developed over the years and you are running in your organizations. They all need to be addressed and remediated, modernized. There are also guidance, some industry-specific guidance, as you can see here, from MITRE, for public services, for GSMA, for telecom, and so on. In the United States, it is now mandatory for all government organizations to report quarterly, every 3 months, to their national security organization, and it was signed by Joe Biden. By 2030, they are aiming to finish this transformation. For all software, firmware, signings, traditional networking equipment, operation systems, and so on. And if they cannot finish, 2033 is the last deadline. And every 3 months, it is being checked by National Security Organization. What we need to do? First, we need to understand which data, which systems are critical in our organization. We need to create these heat maps. We need to put a strategy together, where we will start from, what we'll do this year, what we'll do next year. We need to have a roadmap. Then we need to have a discovery. We need to understand cryptography usage in our organizations. We need to scan all those source codes. We need to listen to our network, what's been going on in between all those systems, which cryptography they are using, what type of cryptography is being used when we store an information in database. So, and the last step is to remediate and modernize all of them, change all of them with the new standards. So this is my last slide, and my message is the risks are real, risks are here. It is not tomorrow's problem, it is today's problem. We need to start today. We need to identify our cryptographic footprint and discover all those assets in our organizations, and not lose time to initiate a quantum safe program. Thank you for listening, and if you would like to have further conversations, please feel free to get in touch with me on this email or my IBM colleagues here. Thank you very much for listening.